Between these two images, which dorsal fin belongs to a shark and which belongs to a dolphin? That's what we want our AI prediction model to be able to answer. In this video, we will turn raw images into data. This data will be used in the Part 2 video to train an AI model. Our raw images consist of dolphins and sharks. We will find the curve of the dorsal fins of every image. Then we will fit these points to a polynomial function and create two data files to train our model. The resulting polynomial coefficients are going to define the curve of each dorsal fin. All code from this video is available in the repo linked in the description. When working with raw images, there is going to be some manual editing that may need to be done at first. For the entire collection of shark and dolphin images, I manually downloaded royalty-free images of sharks and dolphins from pexels.com and unsplash.com. I made sure to only take images that had the head of the animal visible. This way I can confirm without a doubt that each image belongs to a shark or a dolphin. I then flipped every image to face the same way, so all the images are facing left. Lastly, I cropped each image so the dorsal fin was isolated and centered in the image. This is also how we're going to request our users to format their input image when testing the model later. Now that we've covered how to manually edit the images, let's start coding. To clean up our images and calculate the polynomial values, we will do 5 steps. Edge detection, convert our image into a set of XY points, detrending, removing the right side, and lastly, calculating the polynomial coefficients. This tutorial will only go through the processing of the shark images because processing the dolphin images is the exact same process. Step 1. Edge detection. For our edge detection, we are going to use a public library called Canny Edge Detector. The link to that repo is in the description. The Canny Edge Detector library uses multiple stages and parameters to calculate the edges of an image. First, it applies a Gaussian filter to smooth the images and remove noise. We set the parameters called sigma and the Gaussian filter kernel size. The sigma is the standard deviation of the Gaussian filter, and the kernel size relates to the noise sensitivity. The larger the kernel size is, the lower the detector's sensitivity to noise, or another way to say it is, the smaller the kernel size, the less visible the blur. Second, it calculates the intensity and edge direction matrices. Third, we use a non-max image suppression to thin out the edges. Fourth, it uses the threshold parameters and the weak and strong pixel parameters to identify strong pixels above and weak pixels below these thresholds. Lastly, it uses hysteresis to transform the remaining pixels to weak or strong pixels. Here is a visualized example of this from the Wikipedia page for the Canny Edge Detector. So now let's use this Canny Edge Detector library on our images and see what we get. In our project folder, we have our Canny Edge Detector and its associated utils folder we got from the public repo. We also have our folder of cropped shark images, and we will make a new Python file called cleandata.py to handle the logic of the 5 steps of preparing these images. In cleandata.py, let's import our edge detector and its utils, and also Matplotlib, since we will use Matplotlib to display our image data in graphs. Let's set up our Python files main and create a function called cleanImages. In the cleanImages function, we will start with our step 1, detecting edges using the Canny Edge Detector. Let's load all the images and image names from our shark images folder. Then we can pass those images into the Canny Edge Detector library and store the output in an array. We will use some recommended parameter values for the Canny Edge Detector at first. Then let's loop through our output and save each newly edge detected image in a new folder using the image's same file name. Canny edge detection results in a binary image where edges are white and everything else is black, or in this lookup table, yellow and purple. As you can see, depending on the choice of parameters, some images have too much edges and others don't have enough edges. Let's optimize these parameters for our application so that the edge of the fin is clearly visible without picking up any artificial edges in the background. As an example, let's change the threshold parameter and see how that affects our edges. With a really low, high threshold of 0.001, we have a lot more edges. With a really high threshold of 0.9, we don't have enough edges. Playing around with the different values for all of these parameters can get you even better edges for your images. I found that most of these images get good results with 3 different high threshold values, but for this tutorial, we're only going to use the images that worked with the high threshold of 0.17, which I saved to this folder. So after parsing through the good images and the duds, these are all the images that were able to give us good results. Remember, we're only concerned about the curve of the dorsal fin on the left side, so as long as that part is clean, anything to the right or below it is okay for now. Step 2. This output is simply the image displayed with Matplotlib. To be able to use this data, we want to convert this binary image into a matrix of points, which we can easily do by setting it as an NP array with NumPy. So for each image, we will make it into a 2D array or matrix. I will print out the first image matrix in this loop so we can see what our data actually looks like. Let's make a helper function to print our matrix that prints to a file called matrix pixels. As you can see, it's simply a 2D array / matrix with values of 0 for black and 255 for white. Now that we have this 2D array / matrix, we want a single y value for each x value. To do this, we want to iterate top down from left to right and pick only the first pixel we encounter, sort of like raindrops across the top. The first pixel a raindrop lands on will be stored to our new array of x and y points. This is just one of many methods you can try, with the goal being to get a single array of y points for every x point. To iterate vertically, we will transpose our 2D array, and since image matrices are stored with the top being the lowest index, we will reverse iterate so our end results graph's y values go from 0 on bottom to the top. Therefore, instead of going from left to right, top to bottom, we will treat each row as a column. If we print out these new x and y points, we can see that the graphs are facing left correctly and their y-axis goes from 0 to the max value. You may also notice the image is warped a bit since we lost a lot of white space from the images. Since the image matrices do not define a function, meaning there were several instances where multiple y values shared the same x value, our resulting points will remove any points underneath the top edge of the fin. Step 3. Detrend. From the raw images, it's clear that not all the animals were swimming perfectly horizontal, so in order to make our data more comparable, we will detrend the data to align the bottom of each image. We start by finding our straight line along the bottom. We need our first and last x values and our first and last y values. Then we loop through all of our y values and create a new y array that accounts for the slant. To detrend our curves, this formula simply combines the slope formula with point slope equation. I've linked more details on how it works in the description. Here we see the original points overlaid with that slanted line connecting the first and last points in red. Now we just have to subtract that line from our data points and we will have detrended the curve. After running this, we see the new line graphs in green are better aligned to the bottom more consistently. I'm going to change our new line graphs back to blue. And here's our new detrended line graphs. Step 4. Removing the right side. Since we only care about the left side of our dorsal fin curve, let's remove the right side. To do this, we simply take the index of the max y value and shorten both our x and y array up to that index. So everything past this index is removed. This gives us a nice, clean, single curve. Step 5. Calculate the polynomial coefficients. I'm going to use NumPy's polyfit function to get our least squares polynomial fit, and polyfit1d to create a 1D polynomial class. When you pass the coefficients of a polynomial to poly1d, it constructs a polynomial function that can be used for evaluating the overall fit. We want to minimize the number of coefficients required to fit our curves. The less coefficients, the more our values represent a pattern and we can find similarities between them. If we have too few coefficients, we lose a lot of important features of the curve, and if we go too high, our curve becomes affected by outliers. I found a size of 7 to be the perfect degree for the majority of the dorsal fins. The polyfit function returns these coefficients as z-values, so after getting the z-values, I will print them to a file with their label. For sharks, I'll label it S, and dolphins, I'll label it D. And now we have our data file with our labeled polynomial values that we will use to train our AI model in the Part 2 video, called Python Create an AI Prediction Model Part 2, Train the AI Model. Thanks for watching and see you in Part 2.